start today's discussion. Before we actually start dive into discussion on, hello. So we're going to start today's discussion. Before we actually talk about continued discussion on amplifying circuits, I want to briefly mention that we have two things coming up. Next week, Thursday, we're going to have our third quiz, and it's going to cover chapter 4, mostly transistors, basic transistor operation. And then we're going to talk about, going to cover some calculations on amplifier circuits. So mostly, we're going to, because I align with Professor Huang, we're going to probably going to just cover until common emitter. So other architecture will not be included in quiz 3. And so in 2 weeks, we're going to have our midterm as well. So just to remind you that I've just aligned with the other class that we're going to have covered midterm. Midterm is going to cover chapter 1 to 5. And we're going to have, you can prepare a cheat sheet, meaning that you can A4. Put whatever formula you want. So you bring a cheat sheet and calculator, okay? So if you want to start preparing your formulas cheat sheet, you can start now. But this is very important because I used to have like open book exams. It's actually not as efficient as having a A4 sheets because you would then have all the things that you need recorded on the sheets that probably easier to find whatever you need. So this is just a reminder that we're going to have a quiz next week and midterm in 2 weeks. Okay? Any question with the arrangements? Or you can bring it up with emails as well if you have any questions. Good? Okay, so what we're going to do today, before I actually start on today's topics, I want to make a correction. I make a mistake on ignoring the base current. So on the self-bias stage, we have this RB. So the current, we want to find, this is ICQ, and this is the base current. So the total current coming down from the collector resistance is actually ICQ plus IB. Therefore, we get this equation. And then you can use that to find your ICQ. Okay, so just so you made the correction on last Tuesday's notes. Okay, good. So what we're going to do today, hopefully we could, we have already started a little discussion on various types of, a little introduction on various type of amplifiers. Just a small reminder, we introduced the concept of having, let's say this is your bipolar junction transistors. So hopefully, I don't know if we have time today, but there's basically 3 types of architecture. One is that you have your input coming in. There's this input here. And collector is typically the output terminal for most of the voltage amplification. We're going to explain that a little bit more because output, you typically, for voltage amplification, what we typically want is to have high output resistance in order to provide gain. Because remember, if we look at the gain, it depends on current modulation, and then you transfer this current into voltage. Therefore, you typically want to have your output terminal at this, we typically refer to as the high impedance node. We're going to talk about that a little bit more. But just get a sense that the output terminal is typical for voltage manipulation. You typically want your output terminal to have relatively high resistance impedance in order to provide significant gain. So collector is typically the output. And this architecture is referred to as the common emitter. We already tell you that. We already introduced that. And for common base is that you then have base connected to a fixed bias voltage. let's say this is VB. And then in this case, I will have my input right at here, emitter, and still output at this terminal. That's called a common base. And we're going to see if we have time to enter common base. And lastly, you would then have a common collector structure where the collector is typically at this highest voltage, highest biasing voltage. And then we will then have my input still at the base, but output here. There's actually two names for the common collector. You typically don't hear the word common collector that often, CC stage, or it's called a follower circuit. So if you really understand how the circuit works, you would then know why it's called a follower. It's because it's not for amplification, it's for copying whatever is being input into this terminal. So there's reasons for that. We're going to talk about that later. So hopefully today we could finish the discussion on common emitter and probably start a little bit on common base, hopefully today. So for common emitter stage, we have already give you a brief if I have a simple common emitter stage, what we actually want to do is to generate the two-port equivalent model for all the circuits mostly in order to combine with multiple stages. So as I said, for a two-port voltage amplifier model, if we have time. So there's three key parameters as we already discussed. GM. Sorry. Key parameters AVO. And then voltage dependency is this Vin. Okay? So if I want to equivalent all these circuits into a two-port model, I need three parameters to define this model. So for common emitter stage, we have already built our model. So okay, so if I have a simple common emitter stage, if you remember, we have already established that Q1, if I have a simple loading resistor, if that's the case, then my equivalent VL, sorry. My equivalent model, my equivalent three parameters. Remember, three parameters define this two-port model. So if you want to transform this into your two-port voltage amplifier model, then you define the three parameters. So we already know that for Rn, we insert the small signal model. We did that last week, Tuesday, sorry. You insert a small signal model, and we have already established that if you're looking into the base, you will see an input resistance of R pi. You will then have a gain, voltage gain, AVO, meaning that this is not connecting to anything. Open circuit voltage gain is GM RO in parallel RC, right? And then we already know that my output will be RO in parallel RC. This has been established last week, Tuesday, right? So you know that the three key parameters. The other thing I want to mention regarding this results is that we typically want to, aside from having these results, you want to analyze, as I said, how good is it as an amplifier. So one of the key things is that we already mentioned that it would then have a relatively high, this is considered relatively high because this is beta, if you want to write it down, is GM. Typically, 1 over GM is not a very high number, but I have an amplification of beta. Therefore, this is relatively high. It's not ideal, but relatively high resistance in the overall circuit. So you have relatively high input resistance. We could establish relatively good gain. So this is providing a good gain. Voltage gain. But then this is at the cost of relatively high output resistance. So input and output are both at a high resistance level. So that's not very ideal for voltage delivering, as I said. So typically, we need to add a buffer in order to deliver this if my loading is fairly large or loading current is fairly large. The other thing I want to mention is something called intrinsic. What we mean by intrinsic gain is that if you look at the gain itself, it's typically referred to as my loading resistance. This will depend strongly on your biasing current. So what if I have RC equals to infinite? How do I establish that? If I could build, as I said, if I can build an ideal current source, this will give me the ultimate limits of where your ceilings are. Meaning that if you look at this, this will depend on your RC mostly, because RC is typically the dominating resistance, the smaller one in most cases. But if I have an ideal current source, it's simply ICQ. This is actually more common in integrated circuit solutions. So then, if this is the case, so what do you expect your gain will be? We look at our absolute value. So this will be what? If this is infinite, you won't see it, right? So it will be what? GMRO, correct. So this will simply be GMRO. So we already know what GM is, right? GM is ICQ over VT. And what is RO? Anyone remember on your cheat sheet? You want to put that down on your cheat sheet, otherwise, what is it? What is output resistance for bipolar junction transistor? What is it? Output resistance, come on. VT? No VT. What? Correct. So early voltage divided by ICQ. So if I ask you a question, if you look at this, if it's not a finite condition, meaning that if it's RC dominant, if this is the case when RC smaller, in most cases, RC is smaller than RO. If that's the case, then your gain, your voltage gain is actually minus GMRO, RC. So therefore, in this case, if I increase for example, I increase my biasing current. If I change my ICQ, this will actually increase because my GM will increase. But for intrinsic ceiling, what happens is that this will cancel itself so that it will limit by technology rather than your circuit. So if this is the case, then there's something you can do because I could change my RC, I could increase my RC, I could increase my ICQ. Both of them will then change my gain. But in this case, if this is your ultimate, you're already at the ceiling, that's your ultimate limit, then your limit is independent of what you do in terms of biasing, in terms of choosing your output resistance, doesn't really matter because it was limit by bipolar, I should say by device itself. Typically, for device structure, we refer to that as the technology. So as I said, if you ever go into a project and you design, again, for example, already hit the ceiling, and then your boss asks you that, I want more. For example, the gain is not sufficient. I want higher gain. What do you do? If you already hit the ceiling, what do you do? what do? You ask for more money. Why? Because you ask for next generation technology. So you ask for more money because you already hit the limit. So you need to understand what is doable, what are the limits, and how does one break through from the limit. The only thing you can do from breaking through from the limit is to change VA. And then you change the technology. That's the only thing we can do in order to break the ceiling. Okay, so you want to understand where you're actually within the ceiling, then you have circuit solutions. Otherwise, then you need to go for a technology solution. That's very important as to how you solve a problem or solve your challenges. Okay? So after discussing the simple common emitter stage, we're going to talk about a variation of a common emitter stage, which is very often used, which is called degeneration, emitter degeneration structure. So this is, as I said, this is very commonly used. You see the structure a lot in bipolar circuits. The reason, let me explain why. So I have let's say this is my common emitter stage. So what is being done in degeneration is to desensitize the device. Because we know that a bipolar transistor has exponential current dependency, meaning that voltage current dependency, meaning that if I tweak a little bit, the current would explode by exponential. So how to tone down this sensitivity is by adding a desensitized resistors at the bottom. So by adding a resistance at the bottom of emitter terminal, before it connects to ground, this is called emitter degeneration. So then my circuit will be something like this, V in, V out. So let's first assume that we're still having a constant, just assume that it has a resistive load. If this is the case, then how does one analyze this particular structure? So as I said, by adding RE, you will then, this degenerate circuit would have a less, it will actually reduce the gain. We're going to look at that why it reduces the gain. But then it will then increase, we call linearity. So this is more like, if you think about when we look at the overall, if you go back to look at the overall transfer function of the, let me just draw it. Remember we did briefly go through the analysis of V in, the overall, I should say, the overall transfer function of the amplifier. If I'm having the original version, it will look something like this. Remember, if you think about it, it's an exponential dependency, therefore it drops very quickly and then it saturates. So the white is a typical common emitter stage, like this. This means that my transistors operate, this is the operation region, my stage. This is the exponential dependency, therefore it drops very quickly, meaning that my input range are in, so this region is when Q1 is inactive. So the valid operation, I should say this is V in range. So this is very, very small. That would then lead to a problem that is very hard for the circuit to be actually placed at a particular location if there's any variations in input. And also it will make your sound, because the sensitivity is very high, therefore, it's like when I'm holding my microphone very close to my mouth. That would then lead to, if I talk a little louder, it would then reach saturation. That means that it will lead to distortion of the response. So increased linearities, or another thing is that it increases input range. So by adding an RE, if you do the same plot, it will look something more like this. Let me use a different. It will look more like this. This will be a CE with, if by adding an RE, I could extend the input range to here, so that I would then have a lot of leeway in my standing point. Otherwise, I will fall down of the stage very easily. So this will then relax, but then you can see that the slope is smoother. Therefore, it will then, the slope itself is the gain. Let's say this is the gain, the slope. So a gradual slope simply means reduced gain. That is why you see a reduced gain. But then you would then have a wider range for setting up the point. It will make it less easier to stand at a particular point without falling off the operating stage. And the other thing is that it will then allow you to have, we typically refer to as linearity, or truthful reflecting your signal, because you won't be hitting the boundaries that easy. Once you hit the boundary, meaning that there's distortion in your signals, then that's the thing that we don't want. And the reason why this is affordable is because initially it's very high. Therefore, you are allowed, or you have the room to expand or reduce the gain. So you start with a high gain, then you're a rich person, so you can allow to dissipate a little bit of that. So this is because it has an exponential dependency. Okay? So the main purposes of having a degenerate structure is to increase, like reduce gain and increase linearity, or increase input range. So let's look at how it behaves in a small signal model. There's various ways of doing this. Let me first follow the textbook. It's a little complicated in the analysis of the following structure, is that I want to discuss this first before we actually dive into the following discussion, is that how should I say this? You will see that in the following discussion or analysis, I will sometimes omit this at the beginning and add it back. This is the same thing as the zoom in, zoom out philosophy, is that sometimes it's important or allow you to see the main picture. That is why we ignore something. And then when you look at a different thing from a different perspective, then you need to add it back to fit this particular situation. So you will see, this is sometimes confusing for first learners in these type of classes, is that why does one omit or add it back? So first of all, you need to trust me, and then you go back and then review why this will happen when you learn more, and then you will see why something is added back, or a different type of approximation. How does it work? Okay, so let me start with the small signal model. So basically, what we do is that we're going to, I should say, small signal equivalent circuit. So let's first draw the equivalent circuit of the common emitter with degeneration stage. So the main difference, if you actually look at this, is that I still have my original small signal model, R pi GM and have internal voltage V pi, right? And then this will be, this is external. Let me just make sure that I got it. RC load. And then we have external RE at this point. And my input, instead of having only apply on BE, which is V pi, it will actually be, part of it will be divided on the resistor itself. So then the overall input input voltage is here. Okay? So in this case, I'm doing an assumption just to make our life easier. We're assuming RO equals to infinite first. So let's just to look at its basic or most fundamental behavior. So the first principle behavior of a common emitter stage. How does it affect its gain? So if you look at this, this is my output terminal. Okay, so to find out the overall 3 parameters, we're still going to do the 3 parameters: R in, R out, AVO. So we want to start by looking at the voltage gain first. If you write down the equation, by definition, voltage gain is V out, V in. So anytime you do this, you start by writing down what V out will be based on KCL, KVL. So because I'm omitting the output resistance effect, therefore the current itself will be, what is the current on RC? The current should be this, right? Because there's only 2 terminals, 2 branches, I should say. The current, and then times the RC. Sorry. Okay? And what is the corresponding input? So you want to write input as a function of V pi because this is the unknown. We want to establish relationship between input and output. Therefore, we need to find out what is the relationship between input and V pi. So for V in, will then be V pi. If you look at this KVO, V pi plus voltage at this emitter terminal. So let's define it as VE. And what is VE? VE is the current coming in. V is defined by the current going down here. What is the current going down? It's the same as GMV pi. So this is GMV pi. Therefore, we'll then have a GM V pi times RE. Okay? So then I get an equation which is between V pi and V in. Make sure I don't make a mistake. Sometimes don't see well in the book on the stage. Okay? So simply divide these two, we get the voltage gain. The numerator is GM RC V pi. I'm taking out V pi. And do the same thing for the bottom. The denominator is 1 plus GM RE V pi. Therefore, V pi cancels itself. So then you get a gain of, the final results will then be AVO. For emitted generation stage, will then be 1 plus GM. Okay? If we go back to compare it with a same circuit without emitter resistance, The main difference is that you see this attenuation. So let me redraw this. 1 plus GM RE. Right? So this is the one that is without RE. You can see that it should be consistent. Your results should be consistent. Why do I say that? Is that if what happened is that if my RE equals to 0, it should be the same as this, right? So your equation, when RE equals to 0, this is 1. Therefore, you get minus GM RC. So these are consistent results. You want to make sure that your results should be consistent at any setting or condition. Okay? So this is typically referred to as less gain. How do you tune the tuning? The tuning down factor. So it's like, as I said, if it's a water-saving faucet, that's how much you want to save. How much you want to tone down your sensitivity or tone down your gain is by adjusting this RE. This is your twist. You twist this. You design RE to make sure that how low does you want to go. Or if you look at that curve, if I increase RE, I should then flatten it out even further to make a less sensitive but wider input range. Okay? So let's look at the 2 more parameters under this condition. We're going to go back and put this back in. It's more complicated when it's in. But just to get a sense, in most cases, what happens is that it will then reduce the gain. But sometimes it doesn't. So there's special cases. We're going to talk about that later. But in most cases, you would then view adding an RE will reduce the sensitivity or reduce the gain. So let's look at input resistance. So how does this affect my input resistance? Anyone want to make a guess whether your input resistance will increase or decrease? What do you think? Make a guess before we actually go into the math or the analysis. What do you think? So this is still my circuit. Remember how we test this. The way to test this is that I'm simply going to insert a test voltage, a small signal test voltage, and look at its input current response. Okay? So this is still GM pi. Sorry, this is V pi. So in this test circuit, you're simply looking at the input terminal. So let's take a look at what is your V. So to do these type of things, the definition of Rin in this case is Vx Ix. So what we want to do is to find Vx. So Vx is, once again, V pi plus 1 plus a, sorry, I'm moving too fast. The current flowing down, again, the current coming down is GM pi. RE, right? Current going down emitter terminal is GM pi, because there's only one branch connected to the emitter based on 2 branches, one from here, one from there. So that will be, sorry, I should add another. Did I miss something? Yes, I know. Let me make a correction here. Just to make it clear, it's supposed to be, as I said, there's supposed to be 2 branches going down, so you have to include this part as well. So the overall current should be, it's typically ignored. That is why it's not included. So you should include, the emitter terminal should include both base current and collector current. So if I want to make a correction, let me make a correction first, and then we'll come back and do omission. So this will be another V pi plus, this one's missing, GM. Okay? So if you look at this equation, you're going to add this particular term. So we're going to add, let me see. I'm taking out V pi, so okay. The reason why, let me add it back and then we're going to omit that. Just make sure that I got it right. I didn't get it right. Just make sure I got it right. So you're gonna add this term back. This is typically ignored because that term is much smaller in most cases. In most cases, this can be ignored. Therefore, so let me just add it back before we do anything first. So you then have an attenuation factor of mostly R pi RE plus GM. But in most cases, this is typically much smaller. Therefore, you see GMRE. So sometimes you can, let me talk about that later. Because we're going to do a lot of approximation later. Anyway. OK, so if you go back and look at this, there will be two branches of current. That will be GM V pi plus V pi R pi. Times RE. Okay? So what we're going to get is, what is the IX? IX is actually V pi R pi. Right? I could simply define this by having the voltage across. So then your input resistance will then be Vx is the taking out all the V pi, you'd be 1 plus GMRE plus R pi RE. Okay? And for the bottom is V pi. So what we do is simply ignore these, cancel this V pi dependency, and we get an input resistance, which is 1 plus GMRE. You time the R pi back. Let me do this. So the R pi goes to the top, and then RE. Okay? So finally, what happened is that we could actually make a small approximation. This is GM R pi RE. I'm not making an approximation yet. But then what is this? What is GMV pi? What is GMV pi? Let me write it down. Let's write down all the parameters on your, you need to put it down. So GM is ICQ, sorry. R pi is GM theta. And RO is VA. Make sure that I got it right, right? So make sure that you know these three parameters. So what is GM R pi? What is GM R pi? Beta, correct. You got it right. So then we get Rn becomes R pi 1 plus beta Rn. Okay? This is something you probably want to remember, or at least understand that whatever emitter, the way to look at this is that whatever resistance and emitter, if you want to look in from the base, is being amplified by a factor of 1 plus beta. We can go through the whole analysis, but the more intuitive way of understanding this is that whatever changes in current will then be increased by 1 plus beta times. Therefore, the effective resistance, even because the current is much lower here, therefore the effective resistance will then be boosted by 1 time beta times. This is simply the ratio. This simply reflects the ratio of emitter current and base current being amplified by the ratio between the current at 2 terminals. Okay? So finally, if this is the case, for RO equals to infinite, then we'll go back and then look at output resistance. So the way we test our output resistance, remember we set this to 0. We set input sources to 0 R pi, RE, okay, if this is the case, we want to look at the output resistance coming in. You want to do the same thing, test, you can do the test or just simply look at this case, in this case, Ix. So in this case, because I'm setting my input to 0, therefore you're assuming that this part is an ideal current source anyway. So if this is an ideal current source, then my output resistance RL, should equals to RC in parallel whatever is looking in here. Let's say this is R prime. So if you're looking in from here, this is an ideal current source. Whatever the voltage across it is, doesn't really matter. So you have an Rx prom, meaning that this is ideal current source's output resistance is infinite. Therefore, your output resistance simply, you're looking at only RC, because I'm already assuming RO is infinite. This is when assuming RO. Okay? So let me make a summary. If I'm assuming that I'm ignoring early effect, what happened is that assuming RO, in the special case of assuming RO infinite, your input resistance once again is R pi plus 1 plus beta RE. Let me write down the output resistance will then be RC based on this circuit, And then my voltage gain will then be minus GM RC attenuated by 1 plus R pi RE plus GM. Or let me rewrite this. 1 plus R pi GM. So So what is the relationship between the two? Because we know that this is one over, let me write it down. This is GM. Let me redraw this. So this would then be the same thing, GM RC, 1 plus this is GM beta plus. Let me rearrange this to a better form. So it should be 1 plus 1 over beta GM RC. Okay? So that is why in most cases, because I know that beta is larger than 1 in most cases, therefore, your AVO would then be approximated by 1 plus GMRE minus GM. Okay? I think I jumped too fast at the beginning, therefore. So anyway, the attenuation design is simply by adjusting your RE to make your circuit become less sensitive to the changes in biasing point, for example. Okay? So let me think if I have time for that. Why don't we take a break earlier, and then we're going to come back probably 7 past 11, and then we're going to talk about adding back output resistance. That's a very complicated, that will make our life a lot complicated when adding it back. We're going to talk about that a little bit. Okay? So we'll take a break now. And any questions? 我刚才有稍微讲一下，就是在做电路分析的时候，有很多时候呢，我自己在学电子学也是，我记得我自己学的时候也是觉得说，老师怎么可以这样？有的时候加，有时候减，有时候考虑不考虑。那这个原因就是因为想要让大家先看到它基本的精神，然后呢，你再回去 revisit 的时候呢，那你再把东西加回去，因为你一开始加很复杂的结构，会让大家看不到它基本的特性。所以就是你一开始如果 A、B、C、D、E 全部加进去，你就不会看到主要 factor 的影响。那但是如果我今天一开始先讲话，那大家至少可以看到说这个电路的架构它最主要要做什么事情。那之后呢，这些 complicated 的，我比较就是 special case 的情况，譬如说，等一下我要把 RO 加进去，因为 RO 加进去它会有一个负回授的问题，所以会让这整个特性会比较不一样。那它会在某些地方影响比较大，譬如说它在 output resistance 的影响会比较大，在某一些 special case 影响比较大，所以我们就在那个时候再把它加回来。所以基本的精神你要知道，然后之后呢加进去的 impact 我们等一下会稍微花一点时间讨论，但是会让事情比较复杂一点这样子。那我一开始不想要加的原因也是因为不希望大家看不到它基本的特性。OK， 好，Let's continue our discussion. Before I want to clarify something before we dug into more complicated situation. So, in most of the circuit analysis, there's different level of wraps. If you think about it, I'm just going to give a simple, probably more complicated situation. For example, if I have multiple stages. And then I have my biasing circuit, for example. And then I might have my sources. So this is my sources. There might be other source resistance. For example, if this is your circuit, So how does one approach this type of analysis, the input and output relationship? I have multiple stages. For example, I have 2 transistors, let's see, Q1. So I have biasing. I have a common emitter. I have a common collector, for example. This is a typical amplifier circuit. So then how does one approach this type of things? What we do is that, first of all, you want to divide it into stages. So here we're going to generate, this will then be equivalent to a Thevenin equivalent, for example. So this will be, then you then generate it as a R Thevenin, because this is single port, V Thevenin, right? And then in the middle, we want to generate a 2-port model, right? So you want to generate a 2-port model, R out, AVO, V1. And then in the last stage, you want to generate another 2-port model. So how does one generate 2-port model? You insert this with a small signal model. So you insert these transistors with the same model, R pi, GM B pi. Okay? So once you insert a small signal model, you can generate a 2-port model, and then these 3 will then link together. So this will then be another 2-port model, V2, R into, so this is what we ultimately try to achieve. AVO2, V2. So this will then be AVO1. You will then have 2 2-port models or multiple 2-port models. And then you link all of them together in order to get the input and output relationship of the overall system. So there's different level of wrapping, as I said. We have a transistor, we all understand physics, and then we use this model to describe this. And then each stage, you generate a 2-port model in order to link multiple stages. So you simplify this complicated biasing circuit with Thevenin equivalent, 2 2-port models, and link them together in order to get, this is your ultimate VL as a function of Vs, which will be embedded into this Thevenin equivalent model. So this is ultimately what we'll hopefully be able to get to at the end of this class. So you should be able to use these tools at different level of wrappings in order for you to analyze these circuits, or more complicated, with multiple stages. Okay? So the other, I should say, difficulty or challenges in this type of model is that what to omit or what to include in the discussion, it will very depend on this. I should say it would depend strongly on what type of situation or what type of setting the circuit is being put under. So let's go back and see our previous analysis is that we assume early FAD, ignore early FAD, meaning RL is infinite. What if you consider a finite, what is a finite RL? So what is the implication on our 2-port model? So if with finite RL, what should the AVO, Rin, RL be? So first of all, let's just draw the model itself. R pi. Remember, I'm having a degenerated stage. I have GM once again, the V pi is described as the voltage across R pi. And then the main difference is that I'm adding this RO back. Okay? So one of the good thing is that it does not affect input resistance because the input terminal has very little to do with the output impact. So that so what I want to do is that first we're assuming that your RC, in this case, I'm just going to assume that it's not connected to any output. So you sort of break this away. I want to look at this output resistance without combining the output, without combining this RC. So this is when you wrap the outside. But we're just assuming that in this case, we're looking at only RL prom, where RC is infinite. Or you can assume that it's connected to an ideal current source. Okay? So we're going to look at this particular case. So by assuming your output, let me just say that. We want to find RL prom by assuming output is open. Okay? So if this is the case, let's look at AV. It is a little bit tricky because if you think about it, when your output is open, this would simply means that the current going out, I/O, when output is open, meaning that I/O equals to 0. So what does that imply? It will imply that the current coming down here is basically 0. Right? The current, this is open, so this voltage, the current coming down is basically 0. Right? From this branch, because this is, if you wrap it all together, right? So this will be open. This open simply means that this terminal is open, right? Because this is the same terminal if you wrap it together. So this will simply tell us that your input voltage, once again, let's look at input voltage. Will simply be V pi plus current going down is V pi RE times RE, right? That's your input voltage. So what is the input voltage will be voltage across here and voltage across here. The current flowing down will be only the base current because this is the base current. The emitter, because this side is open, you assume that the collector, there's no collector current change because I'm opening this output. Okay? So this will then be 1 plus R pi RE V pi. And what is the output voltage? Your output voltage will then be the current going through RO. So what is the current going through RO? What do you think? The current going through RO, because this is open, therefore the current going down, this direction is minus GM V pi, right? So this will be minus GM V pi RO. I should say RO. This is the voltages cross here, and then we need to add this back. So this will be R pi RE V pi. Okay? So then I had these two equations. See, what is typically being done, most of the procedure is that you write down V in, you write down V out, all in terms of V pi. And then simply divide them to get the gain. So we can get the gain, your voltage gain, in this case, by definition is V out, V in. Let's make sure I don't make a mistake, because I don't have my notes with me. So you then have 1 plus R pi RE. Please help check. And then I will then have a minus GM V pi plus R pi RE V pi. Wait, did I get it right? Okay? Did I miss something? Which one? Oh, V out. Oh, okay, sorry. Yeah, thank you. Yeah. So this is minus GM RO. I'm just going to take out all the V pi term. Right? This is V out. And top, the numerator should be V out. The bottom is 1 plus. I'm just taking out R pi. Okay? So you will see that it will be significantly different. So what we can do is you can actually add them back times the R pi. So this will be R pi plus RE. And then this will be minus beta RO plus. Okay? So this will be very significantly different from our previous results, because it will be then. Let me make a approximation. So in most cases, what happened is that let's just do a special case. So for most cases, we'll have RE R pi much larger than RE. So your voltage gain in that case will then be approximated by, you're ignoring this component. This is much larger than that. You could actually ignore that. So let me write it down here. So just to make sure you know what's being approximated. Beta RO plus RE. You then have R pi plus RE. So we know that this is typically much larger than RE. You typically add a small resistance in an emitter to attenuate the gain. So RE is typically very small. So if that's the case, then you ignore this, ignore that. This is much larger because RO is already a large number and it's beta times larger. Therefore, you will get a result minus beta R pi RO. So what is this? Once again, beta R pi, that's what? Correct. So surprisingly, when you're not, if you open the output, meaning that if you're connecting to an ideal current source, if this is the case, this is simply this circuit. If this is your circuit, you're using an ideal current source to bias your circuit. what happened is that there's no attenuation of gain. This effect simply doesn't exist. We're going to explain that in just a little bit more. So this is a very special case, is when you have a totally ideal current source, and typically when this loading resistance is much, much larger than output resistance, this is what happens. So if this is much, much larger, then you will see that RE effect will be no longer existing. There's no attenuation of gain. You still have very high gain. And the reason for this is we need to look at other parameters. We need to look at one of the problems with having resistors at the bottom of a transistor is there's an amplification of output resistance. Let's look at that in a bit. So let's look at R out. You can do the input resistance part on your own, but this will be very similar to the previous one. There's a little correction, but very little. So input resistance will be very close to what we have in previous analysis. There will be minor correction. So input resistance will still be the same, almost the same. Significantly affecting two other parameters. As I said, the input resistance is very close. The output resistance, the gain is being returned back to typical case when you consider RO and when your output resistance is infinite. You're assuming that your output is open. Let's look at the output resistance when with finite I'm doing a plum simply to indicate that it does not include collector resistance. So this is when we're not including collector resistance. So if this is the case, let's look at what happened. So let's see how you find out your output resistance. This will be a tedious exercise because it's relatively complicated. So I'm looking at add this collector node without consider the effect of R out, RC. So if this is the case, then so how does one find this out? This is when we consider given a test voltage and looking at its test current. Okay? And make sure that we'll put it into here is 0. You're setting the input sources to 0 when we test the output resistance. This is how you test your output resistance. So because there's a finite RO, therefore there's a bridging between emitter and collector. There's no longer, remember in our previous analysis, we're assuming that it's an ideal current source. No, it's not. It's not ideal because there is a finite slope on your collector current versus VCE characteristic. So if you want to include the early effect, then there's a linkage between the two. So how does one approach this problem? So you start by, always start by writing down your current and voltage relationship as well. So first of all, what defines the voltage? The voltage between the two is defined by the current passing these two. But I already know that the current passing through this branch is minus V pi R pi. Right? This is V pi R pi. Okay? And what about this branch? This voltage, I already know that this voltage, because this is 0, therefore this voltage is minus V pi. Therefore, current passing through the emitter resistor is minus V pi RE. Okay? So I already know this voltage. I already know the overall branch current at this terminal. So we know that the current So then you can define the current passing through RO. So the current passing through RO will simply be this 2 current minus this. So the current will be the current passing through this and the current passing through RE. If I'm defining this direction as positive, this 2 current minus that will be the current passing through RO minus GM V pi. I'm not sure I can get it right. Just make sure I don't make a mistake. Okay? Once again, you find out the branch currents. Because this is 0, I know that base current is this. Inverse of base current. Emitter current will be minus V pi. This is minus V pi divided by RE. So these 2 currents minus that will be the current passing through RO. Allow us to define the voltage across emitter and collector. It's very hard to define because it's typically undefined when you have an ideal current source. So then Vx will simply be the current, this current. Make sure I copy it correctly. You can actually do this exercise on your own, but let's just do it today. So this will be the voltage across collector and emitter. And then plus what? Plus a minus V pi, right? Minus V pi is the voltage at the emitter terminal, right? So you define everything as a function of V pi, again. And Ix will then be what? Because the current coming in, you block this all as the same node. So current coming in should be the current going out, right? Okay? So Ix would then be minus V pi. Let me just write it down. R pi minus V pi R. Okay? So there you're in very good shape because everything is in V pi. So then what we need to do is just to simplify RL. So by definition, the output resistance is Vx Ix. So then I'm taking away all the V pi's and taking away, everything is a negative, so you just add it back. Add the positives, so the denominator is 1 R pi plus RE, right? And the numerator will be RE plus R pi plus GMRO. It will be RO. Did I miss anything? I'm putting back RO. Make sure that all the terms are uniless at the top, right? Because this is V pi, the relationship between Vx and V pi. So the numerator should be uniless. This is a ratio, this is uniless, this is gain. And I'm still missing a 1, right? Plus 1. Okay? So it doesn't look like much, but what can be done is that typically what we want is to simplify the factors. So can be done is that I'm not sure I'm getting it right, but hopefully. It's typically very complicated at the beginning, but then it will be simplified. So you simply get this term out. What is this? Wait. And then I'm having RE, RO plus R pi plus 1 plus GM. Okay? So then, what is this? Yes. This is RE, R pi and RE in parallel, this term. Let me write this. This is R pi and RE in parallel. And what is anything? Let me try to write down the approximated results, the final results. So then your simplified results will be something like this. R out will be R pi in parallel RE. And then you has an amplification factor, which is 1 plus GM RO plus, you can get out the RO, and this will be RE in parallel. R pi inverse of the parallel results. I don't know if you can get it. Right? You simply take out the RO. And then let me get the final results. Let me make sure that I get the equations right. So the final results will be, you can take out the, I could actually take out by this, I can take out the RO to make a simplified result. Let me get the results. After rearranging these, you should be able to get this result. Just make sure that I got it. Okay? So what does this imply? This implies that my output resistance actually is very much boosted by this emitter. It will be limited by its own output resistance, but then it will be additionally boosted by this emitter resistance will be additional boosted by this emitter resistance. This is very important when you're stacking transistors. We're going to talk about cascading structures later. But then the main consequence of having a resistance stacking at the bottom of the emitter will be this feedback. This is actually related to a feedback loop gain. 1 plus GMRO, it's a loop gain. And this gain will then boost the overall resistance you can see at the emitter terminal. So this is actually the resistance at emitter terminal. If you can actually see this, if you're looking down, it's RE, looking up is R pi. So these two are in parallel. When we test it, you see the two resistance in parallel. So that's the emitter resistance, the resistance you can see at the emitter terminal. And at this particular emitter terminal, it will be boosted or amplified by a negative feedback structure. So then it will boost it by 1 plus GMR. Okay, so what does this output response, what does the results suggest? It will suggest that if there's various special cases, in most cases, as I said, in most cases, GMRO is much, much larger than 1. What's GMRO? GMRO is VA divided by VT. So for a typical VA of like a 20 volt, for example, it's about 700. If you think about it, GMRO, once again, GMRO equals to VA divided by VT. So as long as your VA is typically like, if it's 20 volt, then this will be approximately 780 something, 784. Just get a number. So it's a very high number comparing to this. So So in most cases, you can simplify your equation by, this is much larger than this. So in most cases, R out can be simplified as R out. And again, two things. And in most cases, RE is smaller than R pi. This is mostly true. So this is when you're designing your circuit for emitter degeneration. The other is that you're not using a very poor, not using your own device, for example. You have a very low early voltage. Typically, this is a very large number. So what happens is that then your R out can be simply approximated as RO plus GM RO plus RE. Okay? So then you will see this equation much more often. Okay? So you see this term again, GMRE, meaning that it's being boosted by a factor of 1 plus GMRE. So you're having the boosting factor of your original output resistance being boosted by 1 plus GMRE. Okay? So if you look at the reason why, let me just give a more hand-waving result as to why our previous results shows that with finite RO, your output voltage gain, where's my voltage gain? The voltage gain is actually very close to, right here. My voltage gain is actually very close to, as I said, it's very close to GMRO. The reason is because of this boosting effect. Let me explain why. Where's my voltage gain? The finite R out. I didn't actually put it down. I thought I put it down somewhere. Oh, right here. The reason for this, I want to try to explain this a little bit. So once we establish the model, let me use the two-pole model. So we already have with finite RO, our two-pole model will be refined as Rin. Is this still the same? So with the finite RO, you would then have a two-pole model looking something more like this. This is V1. Right? So if I'm refining my results by connecting this back to the resistor, back to RC, then what happens is that you insert this resistance back by adding a load back to the circuit. Then this would represent the circuit. This circuit, right? This will then be equivalent to that with finite RO. So the three parameters are Rin is the same again. It's R pi 1 plus beta Re. Your AVO will still be minus GMRO, approximately. These are approximate. It's going to use an approximate number. And then I would then have my output resistance will be RO 1 plus GM. Okay? I'm using also the approximate because if you consider all, it will be much more complicated. So we're assuming that it's under the condition where RE is much, much smaller than R pi for most degenerated design. So what will be the ultimate results at this particular circuit when this is being added? So your new output is, rather than in an open circuit case, is when resistance RC is being added. So if you're looking at this particular point, this will be a V out prom when RC is infinite. So you add it back. So let's look at what is the ultimate gain in this case. So your output V out versus V in. V in is still here. We'll not consider the input effect. So this will be AVO. Based on this model, V1 times RC plus RL. Okay? So we know that V1 is V in because there's no source resistance. Divided by V in, sorry. So this two cancel itself. Then you're approximately getting, this is minus GMRO. This will be RC over R out, approximately. Because in most cases, in this case, my R out prom is much, much larger than RC, right? So then this will be RC over R out. You're ignoring this because, okay? Then we're getting the results. I'm trying to get to the same results as before. So your RC is the top, and this will be RO 1 plus GM. So I hope you see what we're getting at. This is canceled. Okay? So what this is implied, it implies that when you're considering R out, as long as your output resistance, your whatever loading resistance, much low, it's dominant resistance, you're going back to your original result. This only happened, this particular case is only true when I'm having a very, very ideal load, or this resistance is very, very large. When this one dominates, this resistance is much, much smaller than that, then you go back to your previous results by ignoring. This is the same as RO is infinite. Right? So you don't actually see the impact. Okay? So the main reason is because as output resistance increases, you see the impact in attenuating the results at this terminal because you boost your output resistance a lot. Okay? So I want to make a small summary is at this equation. We'll go back to look at output resistance equation. RL. The complete equation is this. But typically you're faced with two types of situation. I should say by default, this is a complete equation. By default, once again, GMRO should be, meaning that you're using reasonable technology, should be much, much larger than 1. So this will be RL. This is the first approximation, 1 plus GM RO. Let me just keep it. Okay? or you want to rewrite it as this is typically true. Okay? So if you use this equation, there's very rare case that this will not be valid because GMRO is much, much larger than 1 is true by default if you're using the right technology. If you're not using, for example, you're not using in reverse active or something, setting it wrong. The second thing, so there's two conditions. One is when R pi is much, much larger than RE. This is mostly true if you're designing this as a emitter degenerate circuit. So the purpose is for emitter degenerate. In emitter degenerate circuit, you typically just tweak a little bit. You add a small resistance. Then the output RL, as I said, will then be RO being boosted by GMRE. So you're going to see this term a lot. This is the feedback coefficient. So another scenario is this. We'll see this when we stacking transistors. For example, this will happen when you do this. We're going to talk about that. This is called a cascade. Even though we're not going to talk about this structure, but we're going to mention, we're going to discuss this type of structure later. But in this case, what happened is that you're looking in down from here. Therefore, the effective RE can be a fairly large number. So the effective RE in this case, RE can be much, much larger than R pi. Okay? So this is the case. Then what happened is that you then have R pi, which is smaller than RE. So what do you think this equation will become? I'm using the approximation. So your R out, in this case, in a structure like cascading structure, it will be more like RO 1 plus, because you don't see the RE because it's much, much larger, so it will be GMR pi. So what is it? Again, GMR pi. What's GMR pi? GMR pi. Beta, correct. So the 1 plus beta. Simply beta RO will be sufficient. Okay? So these are the two types of scenarios where putting a resistive component at the emitter terminal would then lead to a very large, this would typically, when you want to do a high impedance node. In what we call a cascade structure. We're going to introduce that, I think, in chapter 9. Yeah. So let me before I let you go, I'm just going to make a summary. Which one should I use? Which one should I keep? And get rid of this. So I want to make a summary on common emitter stage, so you get a sense as to what to remember or what to understand, to make sure that you understand all the conditions. There's different approximation once again, so we're going to separate it into different categories. So I have common emitter and common emitter with RE. Then you have three important, and with RE, there's two categories. Let me put it into a table. So I have two scenarios. One is common emitter without RE. This is without. Let me just don't write it. Just regular common emitter. So in the right-hand side, there's two conditions where one you consider R out infinite. This is when I'm consider R out finite. So I have three parameters that you need to find out in order to analyze with other additional stages. So I have three important parameters. Once again, input resistance, voltage gain, and output resistance. Okay? So this is all under the assumption that the circuit looks something like this, either with or without RE. So this is the circuit we're assuming. This is based on the circuit, it looks something like that. Of course, the resistive load, we still consider resistive load. Okay? So this is a typical common emitter. And in this case, we're lumping it together. We can still assume that this is finite because including that is not that complicated in this case. So does anyone want to help me fill in the form? Fill in the table. Anyone wants to come and just fill? Raise your hand. All right, come on. No? I'm going to call the guy with the... No one wants to help? Okay, this is easy, right? What is this? 大家都不看我。最后快下课了，来来来，填完才可以走。一个人先举手先填。来，对，那个填完才能走来。来，那个带那个橘色，来啦，这你会啦。填一个好不好？帮忙一下。左上角这个你要填哪个？我们来那个什么什么，那叫做冰果嘛。你要哪个？你要哪个？你来填，来。来啦！你不确定没有关系啊，我们再改啊。我也不确定，我常常写错啊。来，错了再改 ，fine。来，给你红笔。你可以填全部啊。来，你的朋友来帮你啊。格子衣服帮忙填。太好，他来帮忙哎！我们最后填完再下课，没有填完不要下课哦。对吗？哎，这个是这个哎。我右边移。不是，这个是这个是没有那个的，没有 emitter 就是没有 RE 的。
这没有 RE。
对，这个是没有 RE， 所以这个要写这里。
所以我这个
对，来。啊，大家都要比较难的，不要最简单的。来，谁来填最简单的？对，你写对了。啊，这个是什么？这 RE 等于0，就你那个式子 RE 等于0。
对吧？那这个是啊。
对，填。好。哎，你们同学好棒哦，都帮我填完。你们没有填完不要下课。你这写很少人看懂哦。不是。等于什么？好，没关系，你写这个 OK，我等一下再帮你修。 哎，太好了，你们好乖哦，好帮忙。对对对，很讨厌，我也觉得很讨厌。好，零趋近无限大很简单。对，它最困难的是，其实是最右边那个 column， 最右边那个 column 是最难的。来 ，R 是什么？对对对对对，中间那个最简单，中间那个最简单。不用，你不用缩写没关系。我等一下，啊，写这个就可以。你写一个 complete， 我等一下再跟大家讲。缩写在右边，刚才就有讲，就是各种不同情况下。对，你对了，然后你只剩下中间，他们两个就要填完了。你们没有人要帮他们？没有，这个没有很难，这个很简单。对对对对对对对。对嘛？你自己写写看哦，这要写漂亮字不容易。好，左边那个，昨天不是今天上礼拜不是礼拜二，没有啦，我刚才有讲啦，我刚才上课之前有 review 一下。来，谁？对对对对对对，太感谢，谢谢，这样大家可以下课。好，我做一个简单的 summary 啊，就是这个是我们刚才 derive 出来的结果。那大部分的情况下，通常啦，这个我们都直接就是写说我们会用一个比较常见，就是这个跟这个相除，它就变成 GM。或者说正常在这个 case， 如果你要考虑 RC 的话，因为它这个是部分，所以如果你把 RC 考虑进去，它就会变成这样。就是稍微修正一下，就大部分情况下，实际上它是比较接近 GMRO 跟就是你把 RC 这个是没有考虑 RC 啊，所以 RC 放进去，它就会变成这样。那这个就是刚才讲，如果你有考虑 RC， 往下看，通常是这样，就是我以前也很讨厌老师这样讲，可是我现在变老师都会这样讲。往下看就是一个 RO， 所以你就看到 RO 跟 RC in parallel， 就这个东西直接有个 RO 接到底，所以你会看到这两个电阻并联，并联嘛，就 RO 跟 RC。那进来往这边看就是 emitter， 往这边看就会看到这个电阻。OK， 那我们来看一下右边这个 case 啊，右边这个 case 呢，就是这边会有一个 R 派，所以你会有一个 R 派，但是你为什么串联的时候，我们刚才讲为什么它会变成1加贝塔呢？是因为你这里的电流，我们刚才讲这边的电流是 IB， 这边的电流是 IE， 那 IE versus IB 是1加贝塔倍，所以比较好的想法是这样，就是说我如果在这边做一个很小的电流的变化，这一点的电流就会变化1加贝塔倍。所以导致这个电压就垫高1加贝塔倍，所以 effective 的电阻看起来就会有1加贝塔倍的放大。所以你从这边看过去就会1加贝塔倍。所以以后我们下周四才会见面。下周四你会看到，如果我从这边往上看，它就会倒过来，很讨厌。就是这是 bipolar 比较麻烦的地方，因为 bipolar 它会有这个连接，就是有这个 ratio， 所以你如果从 emitter 看 base 的电阻，跟 base 看 emitter 的电阻，刚好会是相反的效果。所以这个大家要稍微有一点 sense， 就是说为什么是这样？就我比较希望是你有一个 intuitive 的 sense， 你比较能够去 capture， 不是说到时候你就一直抄公式啊，抄公式万一有一点点变化你就糟糕了。所以你要有一点点 sense 说发生什么事情。那这边比较麻烦，就是它有很多不同的情况啊。那 通常啦，就是如果是左边这个 case 比较简单，就是因为它基本上是 RC dominate 的状态。如果它是 RC dominate 的话，那基本上就是我们刚刚讲，它有一个 attenuation 的 factor， 它会导致电流，就是 emitter degeneration 基本上的概念就是它导致你的电压控制分压，你把它分压分掉嘛。所以你分掉之后呢，所以你对它的控制降低。对它控制降低的结果呢，就是你的对电流，就是我们通常是它有一个叫做等效。如果你用 transconductance 的概念，就是那个 transconductance 等效的 transconductance 降低，你把那个叫水龙头哈变得比较不敏感，它被压制1加 GMRC 倍。那所以呢，它本身的 gain 原先是 GMRC， 差不多接近 GMRC， 它现在被降低这么多倍。那这个是 output resistance 没有关系。那我刚刚想要讲一下这个后面这边哦，这边呢，我们刚刚有做一个 approximation， 就是这个最后呢会变成比较接近真实的状况，会比较接近 GMRO。这个是我们假设 RC infinite 哦，这是假设 RC infinite。如果你 RC 加回来，它就会回到这里。就是你如果 RC 加回来就是 RC dominate 的话，这是 RC infinite 就是这个式子，那它 approximate 就是这样。那原因是什么呢？就是你可以想象，我其实有2件事情同时在发生了，一个是我的敏感度降低，就是我对电流的控制敏感度降低，因为我用 degenerate 就是给分压的结果，所以这边加的电压只有一部分加在这上面，所以电流的敏感度降低，就是我对电流的操控降低。可是呢，我同时电阻被 boost 上去。你看这个电阻，我们刚才看右边啊，就是电阻呢 ，output resistance 会上升。然后要知道你的 gain 呢是2件事情，一个是 GM， 一个是电阻。所以为什么它最后哦，就是如果说你今天这边是没有加 RC， 你这边是 ideal， 像这样子的 case， 它会遇到一个问题，它就是它有一个特性就是。你的 overall 的 voltage gain， 这个我稍微花一点时间，就是实际上你如果真的要去看，它其实是2件事情，一个是 GM， 这个是整个 stage 的 GM， 这个 GM 指的是 IR versus VM， 然后呢去乘以 R out。所以如果是这个 case 呢，如果我下面的 R1 上升哦，如果你 R1 上升，会导致什么结果呢？会导致你的 GM， 就是你对电流的控制会降低，可是它同时呢会把 R2 往上拉多少跟降多少的 ratio 是同一个，所以最终呢就会导致你的 AVO 就是 constant。这是我要解释说，当你是用这种 case， 就是当你是 ideal current source 的时候，就是上面的 loading 不主导。可是如果你的 loading 是 R out 是 RC 的话，那这个降低你就会看到它降低。好，这样懂我意思？它其实是有2个东西同时在拉了，一个往上拉，一个往下降，所以最终这2个 GMRE 会消掉，消掉的结果就会得到这个结果，就是它会跟 R1 没有关系，你怎么动也没有用。因为你一个控制力降低，可是你 output 电阻增加，所以2个会同时拉，这是这个 special case。可是正常呢，就是 refer to 这个 case， 大部分情况下是比较接近这个。那当你在考虑 output 的时候呢，会考虑加上这个。所以我稍微勾一下，就是这个大家当然要知道。那然后呢，这个你要知道，因为这2个是一样的。然后呢，大部分的 case 呢，我们会只考虑这个，因为我们通常呢。什么时候要考虑这个 case？ 是当你上面是一个非常理想的 loading， 然后再来呢，最下面呢就是比较会接近是这个 case。那你 output 的时候，因为你 output 是如果有特别的 case， 你有 boosting 的现象呢，通常会这2个我们都希望考虑。那结果是这样什么？你现在这个不用，这个 case 很少发生啊，应该这样说，所以你就全部就不要 ，sorry。但是这个，我跟你讲说，这个为什么会重要，就是到后面会重要，因为你会有叠加的什么情况出现。所以，就电路很讨厌，就是说你什么时候要考虑，什么时候不要考虑。那你一开始考虑太多，就会看到这种式子，你就觉得说他到底在讲什么，就没有 sense。那我们还是希望说，你可以有一点感觉，说为什么是这样。OK。